When I made my first video last year covering chapter 3, this next part was included in the original video, so it made it like 35 minutes long, and people complained about videos that are too long, so I'm going to do my very best to keep it around 20 minutes or even less if I can. So I want to get right back into this material so I can head to Fernandina Beach. So I'm going to continue with this idea of energy flowing in the ecosystem, and it's on page 63 and 64 in your book. Let's do it. Alright, I would like to do a little review, but that, again, that just takes up time, and you want these videos to be short and sweet. But you recall where we left off. This was a food web, and the important things that you learned about the 90-10 rule. 90% of the energy is lost as you go up one spot in the trophic levels, and the importance of remembering that the arrows point in the direction of the energy flow and not what eats what. Alright, well, that brings us to another very, very important concept that you've probably never had before, but we'll talk about all the time this year, so you need to know it. And that is the idea of gross primary productivity and net primary productivity. You'll see it you'll see it in the textbook called GPP, and you'll see it called NPP. You've got to see those letters and know instantly what we're talking about. So let me explain it to you. Gross primary productivity is all of the energy in the ecosystem. The sun's rays come down, and notice that 1% of the solar energy striking the producers is captured. So right off the bat, we have a grossly inefficient system. 99% of the energy from the sun doesn't get used by anything to do with at all. But 1% does do photosynthesis. So gross means like total. Gross primary productivity is the total amount of photosynthesis that happens in the ecosystem. It's the total amount of glucose made. That's important because when we're analyzing ecosystems, we need to know how much energy is being added to it. A desert is not going to have a very high GPP because there's not a lot of photosynthesis happening there. There's not a lot of plants. So that's not a very productive ecosystem. So now you can sort of see where we get the word from. Net primary productivity is the gross minus what gets used by the organisms in the ecosystem. So gross is the total amount of glucose minus the glucose that gets eaten or used up. So it's the energy that's left over. And that's an important concept in an ecosystem because all of the consumers and the other organisms, there needs to be more glucose available than organisms that eat it. Two very important ideas. Gross primary productivity, the total amount of glucose in the ecosystem. Net is the amount of glucose that's left in the ecosystem after all the organisms use what they need to use. And this is showing you different ecosystems and the kind of productivity that they have. So you should be thinking in terms of, all right, what are some organisms that have, or places, I should say, areas that have lots of photosynthesis going on? How about tropical rainforest? It might surprise you that swamps and marshes are very productive. There's lots of photosynthesis happening there. Because it's not just the trees and the grasses and so forth that are in the marsh and the swamps, but it's also tiny one-celled algae that grow in the water that do photosynthesis as well. Tropical rainforest, very high in NPP. And see, this is actually something we can measure. We can go in there and we can measure the grams, calories per meter squared per year. These are measurable things. So then we go down. The tropical rainforest is a little bit better than the tropical seasonal which is a little bit better than the temperate. We're a temperate rainforest, which is a little bit better than the boreal forest, which is the pine tree forests of Canada and Russia. Savanna is a grassland, not a lot of trees. So you can see how the amount of productivity goes down, as we look at this. And it should not surprise you that deserts, tundras, and deserts don't have very much productivity. Now let's take a look at marine ecosystems, and the coral reef leads the way. And now you know why we care so much about protecting them. We're trying to protect the NPP. We're trying to protect the amount of glucose that's being made in the coral reefs. Salt marshes also have a lot of grasses and so forth, so they're going to have a high NPP. But then the amount of NPP in the ocean tails off considerably. Only the tiny microscopic organisms on the surface can really do photosynthesis once you get out into the open ocean, for instance, because light will not get far enough down for the plants that are on the ocean bottom to do any sort of photosynthesis themselves. So this is just as you would expect, I think. And so you should look at a graph like this and be able to interpret it, to understand why swamps and marshes and tropical rainforests lead the way, why forests in general are the top producers when it comes to glucose, as compared to grasslands, which are down here, and of course compared to water ecosystems. Okay, we can depict the movement of energy with a food chain or a food web, but we can also depict it through the use of pyramids. Because of that 90-10 rule, a pyramid is a great way to depict the energy flow. You have a big wide base at the bottom of a pyramid. That's the producers. But then when you go up one level to the primary consumers, 90% of the energy is lost, so you only have 10% left. So we can depict energy flow by the use of a pyramid. I'll show you a picture of that in a minute. Well, there's a picture in your book as well. You probably saw it when you did your outline. It's not just energy. The same 90-10 rule applies to the amount of physical tissue that's in the ecosystem. That's called biomass. Biomass is the amount of actual living tissue in the ecosystem. So you're going to have 90% more plants than you're going to have animals. So when you go up one rung to the primary consumers and you measure their weight, you measure the physical amount of mass of animals in the ecosystem, it will be 90% less than the amount of mass of all of the autotrophs, of all the producers. We can also not just use biomass, but we can do this with the number of organisms that are in the ecosystem. Also follow a 90-10 rule. We can use trophic pyramids to show what ecological efficiency is in the ecosystem. So let me just get you to some pictures so you can see what I'm talking about. This shows all three right here. It shows a pyramid of energy flow. All right, down here at the bottom, this is the available kilocalories in the ecosystem, 10,000, and that's all of the producers. And then 90% is lost, so we only have 10% up to the next area. There's 1,000 left for the primary consumers. In the case of this picture, it's zooplankton. And then the perch eat the zooplankton. Another only 10% available. And then the human that eats the fish. Another only 10%. 90% lost at every level, just like I said. Well, that's an energy pyramid, but we can do the same thing with a biomass pyramid. We can measure the actual amount of creatures, the weight of them. You could measure the tissue, the mass of them. And the 90-10 rule will also apply. There, if this is 10,000 kilograms of tissue down here with the producers, then there's only going to be 1,000 left up here. 10%. And if there's 1,000 kilograms of zooplankton, there's only going to be 100 kilograms of fish. So whether we're talking about energy flow or biomass, it also works for the actual number of creatures. If you count all the microscopic little phytoplankton, there's going to be 90% more of these creatures than there will be of zooplankton. This rule of thumb, this 90-10 rule of thumb, occurs whether you're counting the amount of energy in the ecosystem, whether you're counting the amount of kilograms in the ecosystem, how much things weigh at each level, or whether you're actually counting the number of organisms in the ecosystem. The 90-10 rule applies. Now, this isn't just some theoretical thing. We can measure. We can go to a place. Here's what environmental scientists do all the time. They'll go into an ecosystem like Silver Springs, and they'll go in there. They'll measure the amount of kilocalories that's being released from the sun, or the amount of kilocalories that's landing in Silver Springs, Florida. And then what happens? Well, right away, remember we saw in a previous diagram that this is even worse than the 90-10 rule. But almost all of the energy that comes from the sun isn't even used. It's not harnessed at all. It's just lost. But out of the 1.7 million kilocalories, only about 20,000 is available for the producers. The producers do their magic. They do photosynthesis, and then the herbivores come around, and it's time for them to eat the producers. Well, remember the producers started with about 20,000, and now the herbivores are left with about 3,000. 4,000 of it ended up in plant waste. 13,000 was lost as heat, because that was the second law of thermodynamics. That's not exactly 10%. That should be 2,000 if it's exactly 10%. So you get the idea. It's a rough estimations, but the 90-10 rule usually applies. The 10% thing really works here. The herbivores have 3,368 kilocalories, only 383 for the carnivores. That's almost exactly 10%. And then you go down to the top carnivores, that's even less than 10%. You expect that to be 38 in the 90-10 rule, so there's even less there. So it doesn't follow exactly, but these are all measurable numbers. We can measure how many kilocalories are in the waste of the second level, the second trophic level. We can measure the amount of kilocalories in the waste, and we can measure how many kilocalories are lost because of the second law of thermodynamics. And in fact, if you do all of this math, you can keep track of everything that's happened here. Remember the 20,810 that we started with from the sun? Well, when you add up all of these numbers, there's the 20,810. Remember how much was lost that we never used? Here it is over here. So we can account for all of the energy in an ecosystem. And don't forget, by the way, I forgot what I was going to say. Energy in equals energy out. That's what I was going to say. So you're never going to have, if you're accounting for every kilocalorie, you've got 1.7 million here. You've got to end up with 1.7 million at the other end. The problem is only 20,000 of that got used for energy. The rest of it was lost. You could look at the pyramid this way too. Same idea. It's showing you the kilocalories in a pyramid form instead of in a diagram. So I'm just trying to impress upon you this is not a theoretical thing. It's something that we can actually measure. And again, here's another pyramid just showing you 10,000 joules of energy in the grass, only 1,000 is available for the zebras, and out of that 1,000 for the zebras, only 100 is available to the lion. Remember which way the arrows would be pointing. They would be pointing upwards. And lastly, here's a pyramid of biomass. Remember, this is the amount of actual physical organisms in the ecosystem. And I wanted to show you that there are, from time to time, exceptions to the rule when it comes to biomass. When it comes to an abandoned field, you're going to have a ton of grasses there, and so there's going to be way more grams of producers than there is like rabbits, bunny rabbits, and squirrels and things like that that are running around, and then even less of the secondary consumers and so on. But the ocean is a little bit different because there's not a lot of producers in the ocean, but there are a lot of fish. Now, these producers produce enough energy so that the energy pyramid looks normal in the ocean, but the biomass pyramid is oddly shaped because there's just not a lot of, you could weigh all the producers in the ocean, and they're all tiny little phytoplankton and algae, so they don't add up to very much mass at all compared to the fish that are eating them. So the primary consumer part of this pyramid is higher. So I just wanted to point out to you that there can be exceptions to the rule, but you've got to remember that 90-10 thing. Okay, this is where I ended the video last year, and so I'll end it again. I've cut one video into two just for you because I give and I give and I give. The next things that we're going to have to learn is all about the different cycles in the biosphere. You've got to memorize them. 5 that are on the ACE exam and on the AP exam. Water cycle, that's easy. Carbon cycle, you've probably already covered that before. The nitrogen cycle, you may have been introduced to that, but you're probably going to have to rememorize it. The phosphorus cycle and the sulfur cycle. 5 cycles, and I'm probably going to have to divide them up into 2 videos. So, let me say goodbye. And I got to drink some water because my mouth is dry. Hope everything's good with you guys. You have any questions, text me, call me, or make sure you bring those questions to class tomorrow. Goodbye.